Hello, welcome back to Calc 2. This video is just a short review of limits that will really help you out in Chapter 10 if you don't have a good grasp of your limit function. So some of this I'm just going to go through kind of quickly, but just reminding you of those common limits and reminding you of some procedures of how to find limits if you get stuck. As again, you're going to need these as we go through series and sequences throughout chapter 10. So let's just jump right into it. Obviously, the limit as you approach anything, doesn't matter if it's infinity or a number of any constant equals that constant. So first and foremost, if there's the variable isn't even in the limit, it's just a constant. Obviously, then the limit as you approach any value of x is that value itself. Even if that's infinity, then it approaches infinity. Where limits start to get tricky is when you start to put in fractions and everything else. So one of the most common ones used is approaching as x goes to infinity of 1 over x. And that x can be raised to any power. So I'm going to put x to the n, where n could be anything. N could be 1, so 1 over x squared, 1 over x cubed. Keep in mind, your 1 stays constant, but the denominator is going to get bigger and bigger and bigger. And when you take 1 and keep dividing it by a much larger and larger number, those numbers, the resulting number, is going to keep getting smaller and smaller and smaller. And while it will never get to 0, it will certainly approach 0, which is the whole definition of a limit. Remember, it's not going to equal it. 1 over x to the n will never equal 0. But the limit as x increases, regardless of what n is, like I said, it could just be 1, that will get closer and closer to 0. And this can be expanded to polynomials. Such as x plus 3 over x squared plus 6. Keep in mind, and notice that I have the larger exponent in the denominator. That is important. You're going to be working a lot with limits, so going through them kind of quickly is going to be helpful to you. Now, back in Calc 1, we learned all different ways to kind of go through this, but one of the things you learned is to take the limit and to then divide by the highest polynomial, just the x and the highest exponent in the denominator. So in other words, you'll take x over x squared plus 3 over x squared over x squared. And the idea, this then reduces down to 1 over x plus 3 over x squared over, that was 1 plus 6 over x squared. So again, this was the procedure we used in Calc 1. And then going back to this idea, that one goes to 0, that one goes to 0, that one goes to 0. You end up with, in this case, a 0 over 1, which equals 0. And the general idea here is anytime you have polynomials, if I had x squared plus 2x minus 3 over x to the 5th plus 5x cubed minus 7x squared, it's 0. Because your exponent in the denominator is larger than your exponent in the numerator. If you had to, you could go through this whole process to show that it's 0. So understanding when a limit going to infinity equals 0 is important. In the same vein, if you had the limit as x goes to infinity, and let's suppose we had the same exponent, 2x squared plus 3. All right. Again, if you were to divide everything by that x squared term, right, you'd have over x squared over x squared. And we can divide everything by over x squared because essentially what we're doing is multiplying by this, We're multiplying by 1 over x squared over 1 over x squared. Well, that is just multiplying by 1. And when you distribute it across everything, that's where the dividing everything by x squared comes from, right? These are our little shortcuts we learn. And as you're progressing, you can kind of start to do these shortcuts in your head. Oh, well, that's just going to give me a 3. So what does it reduce to? 3 plus 5 over x. 2 plus 3 over x squared. Again, that goes to 0, that goes to 0, and in this case, we end up with 3 halves. So the general idea here is when your exponents, your highest exponents are the same, your limit as x goes to infinity just kind of ends up being those coefficients. So this is the concepts of limits you want to fully understand as we progress into this chapter, and we end up taking a lot of limits. All right, so let's one last look at what happens if the higher exponent is in the numerator. Well, I'm thinking you can see it right now. If I divide everything by x cubed, which is again my highest in the denominator, that's what you want to divide everything by. If I do that, I get x plus 2 over x cubed, 1 minus 1 over x cubed. Again, 0, 0. So it essentially is the limit of x as x goes to infinity, which comes out to infinity. So when the larger exponent is in the numerator, we just get infinity. So understanding those 3 rules will come in handy as we progress through this chapter. Also, understanding all of your exponential functions. So for example, the limit as x goes to infinity of e to the x. And if you don't memorize these, you've got to be able to picture that e to the x graph. Everybody can picture the graph hopefully in their head and can see that as x increases, this just grows without bound. It continues to increase and goes to infinity. And it doesn't matter if it's the base is e, the base can be any value, right? 2 to the x equals infinity. All right, 3 to the x, 4 to the x, 5 to the x, anything to the x is going to equal infinity as x goes to infinity. Okay. So do make sure you know your various exponential functions. It's different if we were going to negative infinity. Whoops. I just wanted e to the x, not e to the negative x. Because again, if you picture the graph, the e to the x graph, as you're moving to the negative y values, that graph will approach 0. And we can do different variations of that. Okay, if you picture e to the negative x, you know, normally e to the x goes this way, right? E to the x. So e to the negative x goes like this. So it just reverses it, flips it around the y-axis. So in this case, when we go to positive infinity, the e to the negative x is going to go to 0. Know your ln graph. Let's take x to 0 of ln x. That's going to go to negative infinity. And then the limit as x goes to infinity of ln x goes off to infinity because your ln x graph goes like that. So we want to make sure you, especially not so much the 0, but do make sure you understand various limits as they go to infinity. Now, sometimes these tricks don't necessarily work, and you have to apply other methods. We went through in chapter 2, in your textbook, in Calc 1, it was the very first thing you did, various methods. plugging in numbers, algebraic manipulation of the actual problem. If you can, you're working on, you just graph it and take a look at it. There's different ways of solving it, but a common method that came up a lot that we learned after we went through the chapter on derivatives was L'Hopital. So don't forget, L'Hopital can be used when you have a limit as x goes to any value of a function over another function. Because polynomials themselves are pretty straightforward. You just plug in the value and you get your answer for your limit. But when we talk about rational, so we have one rational function over another rational function, limits become a little more difficult. So you use L'Hopitals when both of them come out to 0 or both of them come out to infinity over infinity. And you use L'Hopitals by saying, okay, the limit as x goes to a of my two functions, f of x over g of x, is going to equal the limit. And this is important. You usually have to tell, especially on a test, let us know your instructors know you're using L'Hopital. So you put a little L'H over the equal sign. And it's the derivative of the numerator independent from the derivative of the denominator. So when I say it's independent, that simply means you are not using the quotient rule. You're just taking the derivative of one over the derivative of the other, and whatever that limit comes out to, the other limit's going to be equal to that. And there's different variations for L'Hopital. It can also be used, I'll add another one up here, if you have 0 times infinity, because you can simply divide by reciprocal. Whoops, my thing jumped. By dividing by the reciprocal, it then would normally cause a 0 over 0 or infinity over infinity, where you can go ahead and use L'Hopital's rule. So here's an example of that. If you had just a basic product, so let's say the limit as x goes to 0 of x times cosecant x, right? So we're going to take this limit. If we just plug in 0, you'd have 0 times, so cosecant, if you can't remember, just picture your graphs. Cosecant is reciprocal of sine. So if this is my sine function, right? We know what our sine graph looks like. Cosecant has asymptotes where it's at 0. Cosecant looks like this, all right? So cosecant, as x approaches 0, is going to approach infinity. All right, so that means I can use L'Hopitals if I take the reciprocal of one of these. So often when dealing with trig functions, it's kind of easy to take the reciprocal instead of multiplying by cosecant x. We can divide by the reciprocal of cosecant x. So what is the reciprocal of cosecant x? Well, cosecant is 1 over sine, so it becomes x over sine x. So these limits are exactly the same as x goes to 0. Then I can apply L'Hopital's rule. And that you can see, I can apply L'Hopital because as x goes to 0, I'm going to get 0 over 0. All right, so that tells me I can go ahead and do L'Hopital's rule, which is, don't forget limit. It does not equal the derivatives. It equals the limit as x goes to 0. The derivative of x is 1. The derivative of sine is cosine. So that's 1 over, as x approaches 0, your cosine function, which is up here, actually approaches 1, and the answer is 1. So that's just a quick way we can utilize L'Hopital's rule. So a couple other little things. An important limit to know. Now this can be calculated using a couple variations of L'Hopital's rule, but an important limit to know is the limit as n goes to infinity. I'll use n instead of x because you're going to see as we get into chapter 10, we're going to be using a lot of n as opposed to x, of 1 plus 1 over n to the n power. Your Calc 1 teacher may or may not have, depending on how much time, applied this to L'Hopital's. You had to use the power rule, convert it to e to the x functions. It was not an easy one to do. It's a little more complicated. So this is one of those you want to kind of put in your vault and memorize. That is the definition for E. And then brought a more general term for that. If you have a value over n raised to some exponent, that's actually a times b. So these are two you kind of want to take the time and just make sure you know them. They're good ones to know. Another little trick with limits that you didn't get in Calc 1, and I'll refer to it when we need it, but this is really helpful, and it has to do with growth rates. You saw this a little bit when we did partial improper integration. I was going to say partial fractions. When we did the improper integration at the end of chapter 8, and we found that the area of taking the integral from 1 to infinity of 1 over x is actually different of taking the area from 1 to infinity of 1 over x squared. 1 over x diverged and it came to infinity, where 1 over x squared, because it converged at a much faster rate down to 0, there was actually, it converged to a value. I believe that value was 1. So this is the same idea. It matters how fast the numerator versus the denominator grows. So this is an expansion. Let me just scroll up a minute of what we did right here. You know, if the numerator and denominator are growing at the same rate, in other words, they're both x squares, we see the limit is just the coefficients. In this one here, the numerator is larger than the denominator, so it goes to 0, where in this third one, the numerator is smaller, so the limit goes to infinity. Kind of the same idea, but with different types of functions. And there's actually an order to this growth rate. And I'm gonna write something down that really does not have a mathematical reason, but I think you'll understand it. The idea is the limit as n approaches infinity, if your numerator grows at a slower rate and your denominator grows at a faster rate, right, your limit is going to equal 0. Makes sense? Because it's growing at much faster rate as you do those divisions of the numerator divided by the denominator. As the numbers get larger and larger and larger, that value itself actually approaches 0. Where the limit as n goes to infinity, when the numerator grows at a faster rate than the denominator, that's going to come out to infinity. So believe it or not, there's kind of a little chart to get an idea of what is growing at slower and faster rates. So let's suppose we have some positive real numbers. So P, Q, R, S, R. positive real numbers. And then I'm going to throw a b in there, but for b to work, it has to be greater than 1. All right, so I'm just using these as a reference guide. So one of our slowest growing functions is actually ln to any power. That is considered a very slow growing function. So I'm going to do this to show that is going to grow. The next thing that's kind of slow is any base to a power. So this is like e to the third, and that x could be anything, could be an e value, could be any value. Now, what would grow faster than those two would be taking their product, right? X to any value, and then ln of any value. Now, the next growing function, larger than x to the p, is if you took x to the p plus some other number. In other words, you know, x to the 5th is going to grow faster than x cubed. All right. This is followed by a base raised to the x power. And that's the base. That could be anything. That could be e. That could be, it's a constant base. As long as it's greater than 1. B has to be greater than 1. If b is a fraction, you can imagine that doesn't work at this point. But if b is a value greater than 1, like e, b could be e, and you raise it to an x power, it's going to grow pretty fast, much faster than, you know, so let's say this, 2 to the x is going to grow much faster than x squared, right? 2 to the x is going to grow. Does that make sense? So this tells you that 2 to the x is going to grow faster than x squared. And you can just try it just by putting in numbers, right? Just right off the bat, 2 to the 5th is 32, where 5 squared is 25. So you can start to see that as those x values increase, it's going to keep getting bigger. All right, so we're not done our list yet. Let's do x factorial. Now, that is something to come across. X factorial is taking, if say x is 5, so if x equals 5, 5 factorial equals 5 times 4 times 3 times 2 times 1. Okay, so that's a pretty fast growing function. Because just imagine 100 times 99 times 98 times 97. Yeah, you get the picture. It's going to grow very fast, but it's not one of our fastest growing functions. One of our fastest growing functions is actually x to the x. All right, x to the x. That is one of the fastest growing functions. I call this an x. Please do keep in mind that we will be using ends a lot as we get through chapter 10. So I'll just rewrite it for you using ends. Not that it matters. Doesn't matter if it's ends or, but you should get in the habit of seeing ends in place of x's. You know, and if you want to see this in action, you can try a couple things. If you put a little chart together, Let's pick an n value. We'll multiply it by a constant, not that that's on there, but just to give you an idea. And we'll do it. We'll just do it with 2's. So n squared, 2 to the n factorial, and n to the n. So notice I'm not doing the ln ones. They're in there and they're good to know, but these are the main ones to really kind of get the idea of, like, that's n to the p is right there. 2 to the n, your n factorial, and your n squared. All right, so let's take a look. Start with the number 1. Well, that's 2, right? That's 1, 2, 1, 1. Really doesn't do anything. Let's go to 2. 2 times 2 is 4. 2 squared is 4. 2 to the 2 is 4. 2 factorial is 2 times 1. That jumps down to 2. And then 2 to the 2 is 4. Again, not that much going on, but what we are looking at is what happens as n increases. So yeah, what's happening with when n is 1 and n is 2 is not quite as important. We want to see a trend. What happens as I get n bigger and bigger, and you're going to start to see that kind of quickly. So we have doubling it, we get 6. This is 3 squared is 9. 2 to the 3rd is 8. Still backtracking a little bit. 3 factorials, 3 times 2 is 6. And 3 to the 3rd power is 27. Again, not too much yet, but when we talk about increasing n, we want to look at values that are much, much bigger. And here you go. When you start to see 4, you get 8, 16, 16, 24, and 256. You can kind of see it starting to increase pretty quickly now. Let's take a look at 5, 12, 36, right? Because, yeah. Don't know. Ask me why I wrote 36. 25. I was trying to do 32. Sorry about that. 120 and 3,125. Right? 120 because it's 5 times 4 times 3 times 2. It's 20, but times 6 is 120. And then 5 to the 5th power. 5 times 5 times 5 times 5. So we'll do just one more. 6, double 6, you get 12. That's what I was doing. I was copying the wrong column. Yep. I know what 2 times. That's what I get for not doing the work, just trying to copy from my notes. 6. So we have 12, 36, 64, 720, and 46,656. So if you didn't believe me that n to the n is the fastest growing function, I think you can start to see it now. So what does this mean? Well, this simply means if I take a limit as n approaches infinity of, say, n factorial over n squared, knowing that n factorial grows at a much faster rate than n squared, you have your faster over your slower. That is automatically going to get us to infinity. All right. Let's do another one. Let's do the limit as n approaches affinity of e to the 1 Okay, so this this E is just a base. It actually kind of falls in this column here. It's a base raised to some value of n as n gets bigger. It doesn't matter that you're starting at 1,000,000 n. And then n is 2, you got 2 million, e to the 2 million. Not matter. Because you're right. In the beginning, yeah, you're going to be much faster in the numerator than you are the denominator because you're starting at this huge value of 1 million n. But what happens as n goes off to infinity? Because the denominator is a factorial, you are still going to grow at a faster rate. And you'd have to get your calculator or your computer to put really, really big numbers in to prove this to yourself. You are still going to grow at a much faster rate. So that is going to actually equal 0. Okay, so these little, they're good to understand, and it allows you to start thinking through limits very different, quicker than you would before, is to understand when limits grow at faster rates. Okay, so that's my little 30-minute, most of it was review, understanding of limits that will help get you through chapter 10.